So our second session is from Milana Bazayeva. And she is currently based at the Cleveland Clinic in the US. She received her PhD in structural biology at the University of Florence, supervised by Antonio Rosetta, sorry. And her current research is to do with MD simulation, both classical and hybrid, with QM/MM level in combination, and also looking into quantum computing and how that might relate to both biology and drug discovery. And her talk is entitled Leveraging Large-Scale Data to Refine and Validate Metalloprotein Structures, Insights into Metal Coordination and Carboxylate Interactions. So I will hand it over to Milana.
Good morning, everyone. Thank you for the nice presentation. So, as already said, I will talk about how you can use the large data that I extracted for this study in the validation of metalloprotein structures. And during this study, it was also possible to highlight some specific metal behaviors in the coordination, especially with the carboxylate interactions. So the aim of the study starts with the literature reporting some great variance between the donor atoms and the metals in the PDB. And this can be caused by different factors, as experimental limits, the poor resolution, also the lack of refinement programs applying by default, geometric restraints between the metal ion and its ligands, and of course, as in every field, errors might occur during every step of the experiment. So in this study, we wanted to deliver some reference distances occurring between the ligands, and specifically the donor atoms and the metal cations, that could be used by the scientific community for the interpretation and the fitting of the electron density maps and during the protein refinement procedures. So what we did is that we exploited MetalPDB. MetalPDB is a database that was created at the University of Florence, and it directly extracts just the metal binding site from PDB. And it stores also extremely important information about every single metal site. So before proceeding with the presentation of my results, I think some notions must be cleared up. In particular, when I refer to a donor atom, what I mean is, as you can see in this picture, we have the metal that is coordinated by 3 cysteines and 1 histidine. So the donor atom is nothing less than the non-hydrogen atom that is within 3 angstroms from the metal and that is directly interacting with the metal cation. In other words, it is the atom that actually performs the coordination through the share of its lone pair or through the charge transfer, as in the case of Th3 chelates. And the ligand is basically any protein residue or small organic molecules that have at least 1 donor atom. So what we did, from MetalPDB, we retrieved all the holocytes. Holocytes are those that actually bind the metal. And we were able to analyze more than 11,000 sites, computing more than 400,000 distances, which is an impressive amount of data. Using an in-house Python script, we extracted the coordinates of the donor atoms and the metals, and we computed the distances. Of course, as you all know, I'm pretty sure, PDBs can have some exception, which needed to be handled. And in our analysis, we decided to keep only the endogenous donor atoms, which are those coming from the proteins. We discarded all the ligands that did not have full occupancy. This is because, as I said before, since we wanted to give out a reference values, we needed extremely reliable data, and partial occupancy could not be of any use in this case. In the treatment of polynuclear sites, we used distance restraints in order to perform the correct assignment of each donor atom to its metal. As for the metals, we did not filter it according to the oxidation state because of the lack of a clear oxidation state distinction, not only in the PDB files, but also in the specification of experiments used on PDB. And as for the carboxylate coordination, the side chain and the donor atoms of the aspartate and glutamate, we took into consideration both oxygen atoms, and we assigned the label of the oxygen delta 1, oxygen epsilon 1, just to the closest oxygen atom to the metal. Finally, we plotted all the computed distances by dividing our data in 4 resolution range. And all the data that I'm gonna show you are extracted from the best resolution range, which is better than 1.5 angstroms. So again, before moving on, I want to make sure also that the idea of a carboxylate group and carboxylate coordination is really clear. So carboxylate has two oxygen atoms. It is a carboxylic acid that is present in its ionized state during the coordination. And the coordination may occur in 2 different fashions. The first one is the bidentate, when both the oxygen atoms participate directly to the interaction with the metal. And on the other hand, we have the monodentate coordination, which again has 2 different binding modes, monodentate syn and monodentate anti. What distinguishes these 2 binding modes is just the distance of the second non-interacting oxygen atom. So, as for results, every single metal has its own peculiar features, extremely based on the electronic configuration. So it is extremely difficult to generalize behaviors, but for the sake of this presentation, I tried to sum up the key features that can represent different categories of metals. So here we have the alkali and alkaline earth metals that despite they of course have every single metal has its own peculiarities, share some common features, and it is the almost absolute preferences to be coordinated by the oxygen atoms, either coming from the main chain or from the side chain. And what they give out are distribution with extremely broad peaks. This is mainly due to the electrostatic nature of the coordination that allows wider distances, let's say, also compared to the transition metals, as I will show you in no time. And there are different behaviors that give rise to one single broad peak or two broad peaks, as you can see here. What is basically changing is just the amount of data that we collected for the second one. And these broad distributions are, you can appreciate them better here in these box plots. And as you can see, all the so the bold line represents the median, and as you can see, sodium and magnesium are those with the most spread data. But in this case, there is also probably incorrectly modeled water molecules that participate to this phenomena. On the other hand, we have transition metals. So transition metals have a completely different nature compared to the alkali and alkali earth ones. And here we can clearly see different trends. So starting with the manganese, as you can see, we have only the carboxylate coordination and the histidine coordination. And also, as reported in the literature, even here, we confirmed that the manganese shows an absolute preference to be coordinated by the nitrogen epsilon to the histidine. And this is probably also occurs for steric factors, since the histidine nitrogen delta 1 is extremely close to the backbone. And then we have the nickel, which is a little bit different in terms of the histidine coordination, since here we have 3 different distances that were computed for the histidine nitrogen delta 1. And this is something that was observed in specific chelate sites that are typical of the nickel. Then we have the zinc. So the zinc is the only metal that actually has one transition metal that has actually just one oxidation state. And so if you look at the values for interactions with the cysteine and with the histidine, we basically have just one single value, and this is because the zinc cannot change the oxidation state, and these interactions are not might be just influenced by the geometry, but still here it is always almost a tetrahedral one. So we don't we did not observe major changes, major behaviors like, for example, nickel, iron, or manganese. Last but not least, we have iron and copper, which are the 2 metals that share some coordination performed by residues that we did not observe in any other metal, which are tyrosine for the iron and the methionine for both copper and iron. Here you can appreciate the differences for the cysteine and methionine coordination, here for the iron, and here the same specific case for the copper. So you can see how the behavior of the coordination changes for the same metal, passing from the cysteine to the methionine, but also between 2 different metals. As you can see, for the cysteine, in both cases, we have extremely sharp peaks with narrow and sharp and narrow peaks, which is something completely different from the distribution that I showed you before for the alkali and alkaline earth metals. And this is due to the soft interaction and to the mostly covalent bond interaction of in these metals. And also in this specific case, when we talk about the cysteine, we have to consider that the coordination is performed through the thiolate group, which has a negative charge, and so there is a huge charge transfer in this kind of interaction. On the other hand, we can see how we have some broader distributions for the methionine, and this is because here we don't have a net charge, but just a coordination performed by lone pairs. And again, here you can see how the behavior changes passing from the iron with extremely sharp peak to the copper, where the distribution is way broader. And of course, these differences are also tied to the different roles of these coppers in the metal binding sites. So proceeding, what we observed, what basically is extremely common and in all the kind of metals that we analyzed so far is the carboxylate binding. And this kind of coordination is extremely important. And for the alkali metals and also for magnesium, we observed extreme preference to the monodentate coordination. Whereas for the calcium, as you can see here, it is clear that all the 3 possible binding modes are are performed. Here we have a bidentate coordination, and here you can appreciate the monodentate syn and the monodentate anti-coordination. And this is something extremely related to the nature of calcium and its role in the proteins, since it must be regulated during the signal processes. For manganese and iron, still all the 3 binding modes are showed, but in this case, like for iron, it is extremely important since the carboxylate interaction can participate into the regulation of the oxidation of the iron. And so it is extremely useful to stabilize reactive species of these metals. For nickel and zinc, we observe the monodentate coordination, and as for iron, also in zinc, the carboxylate shift is extremely important since it participates in the substrate exchange control. And here you can see an example for iron coordinated by the aspartate. Here it's counterpart for the zinc, and here we have the glutamate coordination. And again, as you can see, even in this case, we have different metals and different behaviors of coordination with all three binding modes for the iron, whereas for the zinc, we have a main preference for the monodentate zinc coordination. So since we had extremely wide amount of data, we also decided to take a look into the metal-metal distances, something that we did not found in the literature, and that can be of potential use for experimental people. So we basically observed two different trends. So panel A and panel B. These are two examples reporting the metal-metal distances within 3 to 7 angstroms, from 5 to 7 angstroms, I'm sorry. And what occurs is basically that we have like a carboxylate or a small organic molecule bridging between the two metals, or just the two little water molecules acting as a bridge and coordinating at the same time the two metals. For higher distances, up to 11 angstroms, we have the situations where there is the whole residue, like in this case, the histidine bridging between two metals, and way more extreme case where we have this porphyrin framework with the two metals, but again, it is spaced by this huge molecule framework. Last but not least, to give a complete picture of how the coordination can be performed, we also analyze the water coordination. So it is extremely important, the water coordination, and in most of the times it is extremely difficult to determine when the water is present. And in this study, we were able to do so because of how big our database was, and for the huge amount of good resolution structures that we had in our use. So here you can see different trends for the alkali and alkaline earth metals, with potassium being the metal that but does not really enjoy being coordinated by water molecules. On the other hand, we have the magnesium, which is the metal that shows the higher number of water molecules, with 13% of sites having at least 4 water molecules. Curiously, for sodium and calcium, we have similar trends, similar percentages of sites with 1 or 2 water molecules. And for the transition metals, we have interesting pattern for the manganese, since 56% of the sites have 1 water molecule, and whereas all the other transition metals prefer not to be coordinating by water. So this is what we obtained, and hopefully it can be of use to experimental people, and I thank you for your attention.
Thank you for an excellent talk, and we'll open the floor for questions and answers.
Hello, here Martin Mali, MRCLMB. Thank you for nice talk. I was just thinking, did you try to filter iron 2+ and 3+? But there are some different. I would expect there would be some differences.
Sorry, can you repeat your question?
Yeah, I was just wondering, you said that you didn't filter out different, when some element can have different charges. I was thinking before you didn't filter it, whether you tried to filter, and whether did you particularly try to filter iron 2+ and iron 3+? Because I would expect some differences.
So we did not perform oxidation state filtering because there are no reliable data. So even when the data about the oxidation state are reported, we must consider that the X-ray beam can induce the reduction of the metals, and this can be undetectable. And this is a big limitation in the extraction, in the filtering of the metals according to their oxidation state. This being said, there are techniques that allow to assign correctly the oxidation state without inducing damage. But these methods are not widely used. So even when we filtered on PDB, there is like the option where you can choose the experimental technique. Even when we did that, the amount of data was extremely narrow. So it was not possible to get reliable information as we wanted to give out. And also, there is also a huge limitation in PDB because there are like some specific labels to report in the PDB files the metals. There is a specific label for copper 1, copper 2, copper 3, or even iron. But unfortunately, not always these labels are correctly used. And for some well-known cases of like iron proteins, where the oxidation state is reported in the article, in the PDB file, the labeling were not changed. So even when they had 3 different oxidation states, the label that they used all referred to one specific oxidation state. So yes, your point is completely right. If we had the extremely reliable information, we would observe some differences in the coordination between the same metal ion, but with the different oxidation numbers. But unfortunately, we cannot.
Hi, Mike Huff from Diamond Light Source. Are you able to analyze the PDB and identify structures which have been modeled with the incorrect metal ion?
So this is a good question. Unfortunately, in X-ray crystallography, there could be some incorrectly modeled metals. For us, our aim was not that one of correcting these inappropriate assignments, also because there are other way more appropriate programs like Check My Metals that aims to correct and assign the correct metal to proteins. What we basically did was rely on the information reported in PDB and exploit that. And in our analysis, in order to avoid this kind of situation, we decided only to use the data that we computed from the best resolution range, which again is lower than 1.5 angstroms. So we just kept extremely good quality structures to avoid possible errors.
Hi, Deborah from PDB. Just to bump on that comment, just to let you know that PDB is preparing a big remediation on metalloproteins, and that's going to come in the next 2 years or something. So you will hear about this a bit later.
Perfect, amazing. So I'm gonna run my script again. And finally, we can see these differences caused by oxidation numbers.